Efficiency and thermodynamics. Don't be frightened by the big word. It's really quite easy. You should be able to calculate efficiency from input and output energies and explain why it cannot exceed 100%. In basics, all you need to do is be able to go from percent efficiency to the energy input, the energy output. That's it. Common sense understanding of efficiency will do all this. The main thing is to downgrade any applied energy by given a percent, or given the needed energy, upscale it to what had to go into the machinery in the first place. And we're going to look at the societal appreciation of energy waste. And we can look at efficiency, school grades, error percentages as all is the same thing. Basically, test scores on the various things we're measuring. The cat added a dramatic touch. The father of thermodynamics in terms of machinery would be James Watt. He got the first big machines going. He managed to make the steam engine smaller and revolutionized the world, paving way to the Industrial Revolution, which had some horrific impacts on society. The Ballad of John Henry is an example where the human male became useless against the power of steam. But it turns out the pursuit of a functioning steam engine also predicts the Big Bang and the heat death of the universe. So it turns out a practical concern turned out to have scientifically fundamental understandings to the universe. We use thermodynamic equations in the study of black holes.
Ladies and gentlemen, John Henry.
The true father of thermodynamics would be Sadi Carnot, who was a military figure during the War of 1812 or the Napoleonic Wars, and he put down some of the most theoretical basis of thermodynamics. Lord Kelvin, giving us the temperature scale, was one of the other greats out of about a dozen people that formed this revolution in science. You start touching on some of the core thermodynamics formulas in high school using this one in chemistry, PV equals nRT. I'm showing you the MC delta T, right? My rap star name is MC delta T. I'm here to talk to you about heat to D. And the cat's adding some dramatic music again. Work equals force times distance turns into pressure times change in volume, and you'll learn that in chemistry as well. They laid the basis for the mathematical study of the movement of heat. How does efficiency work in here? The trick became the steam engines were throwing out more of their energy as heat. This was not as obvious with animals as it was with the steam engines. So Carnot wanted to come up with how can I make an engine the most efficient possible? And he laid the groundwork. So in terms of our energy systems, if we look at nature, you feed a cow 100% of its food. It turns out only 10% of it is left on the bones of a cow to make a meal out of. 90% is lost to heat and degraded energy. But in nature, that 90% loss is often made up by scavengers. So today's beef on a cow was last year's poop on the field. So eventually, nature scavenges up a lot of this energy and returns it to the food chain. With our cars are more efficient than life forms. Life forms are about the least efficient you can get as an individual animal. A food chain, including the scavengers and decomposers, is very efficient, but not the individual animal. A horse poops out 90% of the energy you fed it, and only 10% goes to dragging your butt around in your carriage. A car poops out 80% of its energy out the tailpipe as heat. Unfortunately, we have no means of reclaiming that heat and using it, so it is truly lost. But cars are still about 20 to 30% efficient, making them a better choice than horses if all we're counting is joules. But the horse poop decomposes. The car exhaust does not particularly. There's a simple formula for efficiency, but it's bludgeoned to death. You take the energy you actually got out, divide it by the energy you put in, and multiply it by 100. Exactly what you do on a test. I got 63 on the test. The test was at a 75. I wonder what percent that is. But teachers figure you're a complete freaking idiot and tell you, oh, don't forget to multiply by 100. Like that you can't possibly see that 0.63 is 63%. So seriously, why memorize the energy formula or the efficiency formula when all you have to do is treat it like a test score? What did you get? What was it out of? Otherwise, you're going to be one of these hillbillies. I got 13 bullseyes out of 50 shots target shooting. So let me see that 13 out of 50. That's 0.26. Oh, dang, my calculator is done busted. How am I ever going to multiply 0.26 by 100 now? So if you understand the formula, you don't need to memorize it. You just use common sense, and the formula is always with you. So let's take a first example. Johnny decides to use 3 kilojoules of gasoline to fire his pumpkin cannon. And what he found out that only 0.3 kilojoules appeared as kinetic energy. Well, what would 0.3 out of 3 be? That's 10%. You can use the entire formula if you wish, but it's much easier. So sure, set the formula up, but gosh, don't commit it to memory. It's common sense. It's how you do a test score. You got 0.3 marks out of a test out of 3. You suck. Okay? Now, would you get the same answer if you measured the energy in calories? Absolutely. Because look, it's kilojoules over kilojoules. The units disappear. You should not get units left over after efficiency calculation. Percentages have no units. So it wouldn't matter what unit you measured it in, the units disappear. Now, let's say you have that stupid friend that always thinks they're right, and Billy, he says the efficiency is energy in over energy out. How can you prove he's wrong? Well, if you did it upside down, you get 3 kilojoules over 0.3. That's 3,000%. You can't have 3,000% efficiency in our universe. Even the Marvel universe doesn't push the envelope that far. Seriously. If your friend insisted on that, just say, Billy, according to your formula, if you got 3 out of 30 on a math test, you got 9,000%. So if he continues to argue this point, unfriend the man. He's just too stupid. He's going to endanger your life at some point. So Billy comes back. Now he says, oh no, I worked it out. Efficiency is energy in times energy out. And you try to point out to him again that if he got 40 out of 100 on a test, which is clearly 40%, and he says, no, multiply them, you're saying, so you got 400%? Right? Actually, 4,000%. The man is being persistent about his idiocy. Well, what happens if you actually carry out his math? You get 90%. So he's going to argue the point that 90% is a perfectly probable numerical number. But you point out something in blue. If his formula is correct, you now have a percentage, the cat is back, in kilojoules squared. What kind of percent is that? There should be no units. So there's a fairly easy common sense double check on this. Stop with the dramatic unit. You keep stepping on the power button to the piano. Okay. A rocket burns 12 megajoules of energy and is 90% efficient, which is true. Rockets are incredibly efficient. Why don't we use rocket motors on our car? Because setting fire to the people behind you is frowned upon. So how much useful thrust will this vehicle produce? Well, we got a problem with the word thrust. You might go, do you mean the output energy? Yes. So the teachers poorly phrase themselves here. So you go, efficiency is energy out over energy in. We want to find energy out. So we rearrange the formula like so, and we get 10.8 megajoules. This makes common sense. If you had a test out of 12 and you got 90%, your score is going to be around 10 or 11. Now, you want to see how common sense can make it clear, no matter how dumb you feel that day, that you can do this. There are only 3 possibilities with the number 12 and 90. Like, there's literally only 3 things you can do in reasonable arithmetic. 12 times 0.9, which is 10.8, which sounds reasonable. 12 divided by 90% gives you 13. It's like, what kind of 90% student are you if you think 90% is getting 13 out of 12 on a test? That makes no sense. The other possible wrong math you could do is 90% divide by 12, and you get a score of 0.05. And you go running into your brains, I got 90% on the test, and I only got decimal 0.075 of a single mark. So this is what I'm saying. Common sense. If you're thinking about your math, you should start going, warning, warning, does not compute. Now, let's suppose you compute a task requires 10,000 joules of work to do, and you know the engine selected is only 25% efficient. How much energy are you actually gonna need? Well, think about it. You need 10,000, and I just told you the engine you've picked is wasting 3/4 of the energy and only passing 1/4 to you. Is it not obvious that the answer is 40,000 joules, 40 kilojoules? Because 25% is 1/4. And the minute you think of it as a fraction, you're good. As a common sense approach, look at it this way. You are given $10,000 as part of an estate. There are 4 children, including you. Therefore, your cut was 25%, or 1/4 of the whole inheritance. If you killed all of your siblings, how much would it? Oh, sorry. The principal's pointed out again, I cannot do my mafia things. I don't know why. Being an Italian background, I think doing culturally appropriate mafia jokes would be fine. So anyway, don't kill your siblings. So how much was the total inheritance if you got 1/4 of it? Nah, 40,000. A neat conceptual trick. I've been pushing conceptual tricks for you since the beginning of the course to help you be one with the force of physics. Treat mu, the coefficient of friction, as a percent of an object's lifting weight. Pretend any force you see in newtons came from gravity. Divide it by 10 and pretend it's a kilogram mass, and you have an intuitive understanding. Write accelerations as newtons per kilogram when you're trying to understand how force is spread. And now we're going to add to this list of conceptual tricks how to see percents as fractions. Instead of going, I need 50% of a number, say I need half of a number. And then the opposite to go backwards as twice as much. If you get 1,000 joules of work and you got it from a 4% efficient source, what is the opposite going backwards from 4%? Well, on your calculator, you would divide by decimal 0.4. But decimal 0.4 as a fraction is 1/25th of a whole. So if 1,000 is 1/25th of the whole, then the whole was 25 times more. This is something you have to choose to practice. So for example, if I say to you, I want 5% of a number, that is 1/20th of a number. So let's say I said to you, this engine produced 500 joules of useful energy and it was 5% efficient. What was the original energy? You would have to divide by decimal 0.5 on your calculator. But what's the opposite of a 20th? 20 times more. So if I said to you, a 500 joule energy source was only 5% of the original, then you go, oh, 500, 20 times bigger, that's 10,000. Have a look at this and try to see that you can turn fractions backwards to percentages in the reverse. So 20% is 1/5, 2% is 1/50th, 3% is 3 out of 100. The opposite is 33 times. Okay? So this will really go a long way if you bother to implement it. I will not teach you it as a drill because it doesn't work. You have to be willing to start doing this in your head, and you will be slow at first, but you will gain speed like you wouldn't believe. So you have 17,000 joules of energy. The mechanism you use is 15%. How much useful energy comes out? Solution, you would use your calculator, right? No. You can do 15% in your head. Watch. Just take 10% and 5%. 10% of this number is easy. It's 1,700. Then 5% would be half of it again, 850. Add them up in my head, 2,550. And you might go, but geez, Claudia, that took you 20 seconds. Only because I'm describing what I did. But once I get good in my head, you think I'm brilliant when I go, 15% of 17,000, that's a 2550. And you go, how did you do that? It's like I broke it into pieces. I didn't actually do long form multiplication in my head. Here's a second example. A car produced 50,000 joules of energy. You know the engine is 22% efficient. How much total energy did the car burn? You rearrange that formula. You must get a larger answer, right? You're at the output end. So you got two choices with this percent. You multiply by the percent or you divide by it. Which one is going to make the answer bigger? The direction you're going. Divide by. Watch what I can do in my head. I'm going to round 22% to 20, which is 1/5. Okay, so the opposite of 1/5 is 5 times bigger. So the number could be 250,000. What if I rounded 22% to 25%, which is a quarter of the original? Then the original is 4 times bigger, 200,000. So my answer is somewhere between 200 and 250,000. I'm going to guess 225,000. Bingo. And again, you might go, well, that took a lot longer than the calculator. Yeah, but it'll double check and it'll go fast. And the more you estimate in your head, the smarter you feel. Also, when I explain this trick to you, it takes many times longer to explain the trick than it does to actually carry it out in your head. But you have to be willing to try. Now, here's a slightly more complicated one, and it's stuck with instructionitis. A mass of 25 kilograms is lifted by 5 meters in altitude. If the motor used is 70% efficient, how much energy was needed to do the lift? What's wrong with this? You might go, I don't know how to do this because I've skipped an intermediate step. Let's alter that statement to put in the intermediate step that you're frustrated about. A mass of 25 kilograms is lifted by 5 meters. Calculate the potential energy when lifted, and if the motor is 70% efficient, how much energy was needed to do the lift. The sentence in bold is the intermediate step that you're going, I don't know what to do. I don't know what to do. But if teachers engage in instructionitis and always give you the intermediate step, you will never learn how to do it on your own. So you have to go, what are the steps I need to do to get there? So you calculate the potential energy, and this energy is only 70% of the total. This is the output energy. So we need more than that. So 1250 will be divided by 0.7, and we get 1786. Here's a slightly more complicated version of the same. A mass of 25 kilograms is lifted by a motor that provides 3,000 joules at 53% efficiency. How high does the mass get lifted? The problem with this is the teacher has poorly phrased the question. Did they mean that the 3,000 joules went into the device and dropped to 53%, or that 3,000 joules was left over after the 53% efficiency drop had already been calculated? Well, if we look at the English language, and you can see it in the footnotes to the original slide, the hint that provides in an English sentence would seem to indicate that is what the motor actually carried out. So it already provided you 3,000 joules, so more must have gone into it. But the teacher should maybe make that clearer to you. In the first case, if we assume 3,000 joules came out at 53%, then only 1590 was left over to lift. In the second case, if we say, no, the 3,000 joules is actually what we saw go into the mass, then what went in was larger. So this is downgrading the energy, and this is increasing the energy to the original. So depending on which one is the energy left at 3,000 downgraded to 1590 or upgraded for 5660? Well, let's try both. Putting in 3000, putting in 1590, and you get 6.4 or 12 meters. But that phrase, that provides, seems to indicate that 3000 joules came out of the machine. So 5660 went in, and the teacher probably meant this, but that's when you ask for clarification. Waste energy is often routed out as heat in a system. Radiator systems are found in almost all of our appliances: furnaces, fridges, computers, cars, air conditioners. Contrary to Hollywood, astronauts actually run the risk of overheating in their suits because there is no cooling atmosphere around to pump the heat into. So I want you to watch the Bitcoin miner ones and how people can actually heat their houses with their Bitcoin rigs. Computers have a real problem. They are killed by the heat. So they are running about 70 to 80% efficient. Electrical devices are fairly efficient. Compare that to 30% for a car. But it still means the computer is vomiting out about 30% of its energy as heat. A Pentium 4 2.8 gigahertz CPU can reach 85 watts power dissipation at peak usage. This means it's trying to stuff out of it 85 joules every second as heat to get it out of that processor. So if the processor is kicking out 85 joules every second, and this went on for 600 seconds, think about it. If I say I'm giving you 85 pennies every second for 10 minutes, you multiply by 600. So this means a Pentium 4 2.8 gigahertz CPU, which is not a particularly big one, is got to shed out 51,000 joules of heat every 10 minutes. Well, how can we understand? Is this a lot of heat? Let's put it into a cup of coffee, see what happens.
Hey, what's up, guys?
So a cup of coffee is typically 250 milliliters or 250 grams, same thing. So we're going to take the CPU and we're going to fire all its 51,000 joules into the water in the cup of coffee to get an idea of what 51,000 joules would do over the course of 10 minutes to a cup of coffee. So let's say you made a new computer rig where the CPU is on top and you could set your coffee there and let the CPU heat it up. So we're going to fire 51,000 joules into the formula, and the mass of the water is 0.25, and the heat capacity of water is 4.184 kilojoules per kilogram per degree. We shove it into this formula, and we set up for computing delta T, and you get this, and watch. You cannot put kilojoules into the formula. Well, we want joules as an answer. So there's a conversion here. And this gives me a delta T of about 50 degrees. That means the temperature rose by 50. It's not at 50, it warmed up. So tap water is going to come out somewhere between 10 and 20. So you've got a nearly boiling cup of coffee in 10 minutes. The CPU is finished at 110 degrees. It'll start to destroy itself. So yeah, 10 minutes without a fan, that CPU could really overheat. And if we didn't put the cup of coffee on it, it would be a goner long before then, because the CPU doesn't weigh nearly as much as the cup of coffee does. So there's not much there to absorb the heat. So cooling the CPUs is important. And if you watch the Google data center, they have industrial coolers to keep that system from melting down on them. So here's an example how we can assess what energy would mean by simply funneling it into water and seeing how hot the water would get, or funnel it into a 10 kilogram mass and see how high the mass would be lifted in the atmosphere, and you've scaled it. Now, going beyond the mathematics, what can we do with this waste heat? Well, there's a thing called FLIR, forward-looking infrared. Ultraviolet light is too blue to see, like a note so high on the piano scale only dogs hear it. It is very damaging to life, you may have heard. Infrared, or infrared, some people pronounce it, is too red to see. Like a note too low to hear, near infrared is just beyond vision. It is used in TV remote controls and can be seen by some humans. So if you take your TV remote, like mine there, that unfortunately got cat vomit on it, and you point that LED at your cell phone, press the buttons, and your cell phone may record the flash of light. You may see it. If you have a laptop computer, point it at the camera and watch, and you may find that some of your cameras around the house will detect the flash from that infrared thing. You can point the infrared detector away from the TV set and bounce the beam off a mirror. I can even bounce that LED off my polished forehead and reflect it. So many TV remotes have an infrared emitter to control it. Far infrared, way down, low, 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 low in the light level, becomes what's called thermal infrared. It is perceived as heat. In a thermal infrared camera, you see a dog showing up like that. And obviously, thermal infrared cameras are great for detecting losses of heat due to poor efficiency. There are many uses for thermal imaging. Dzhokhar Zarnev was the brother of the Boston bombers that killed innocent people a number of years ago, and he was injured and took to hiding under a boat, and a police helicopter easily looked right through the boat at his body heat. And there's video online, you can see him moving around. So what's invisible to us, the camera can pick up. Medical thermal imaging. The top image is a diabetic person, and the one leg has an occluded artery, so the blood's not flowing, and the leg is cooler. This person has thrombosis, deep vein thrombosis in the leg, so the circulation is severely affected on the one leg there. And that's what nearly killed me. I had thrombophlebitis, cellulitis, and deep vein thrombosis in my right leg. I nearly lost it. And after massive antibiotics and anticoagulants, they set off a heart attack that would have been fatal had I not been in the ICU at the time under extreme watching. And that happened on Friday, December the 13th, 2013, of all dates. So I sort of feel that my life was saved by a bullet being struck by another bullet and saving me. The heart attack was ready to happen any day. And it was just so lucky that I was in the hospital and they triggered it with their treatment and I was able to be saved. So I'm very grateful for that. So since then, every time my right leg hurts, I get a little afraid again. Deep vein thrombosis was painful. This is a standard, you can buy them at Canadian Tire now, a FLIR camera aimed at the house. And you can see in the picture, there's a lot of red up near this window. And so you're seeing heat escaping there. And you can use this to improve your house. If the house is 100% efficient, it wouldn't show up on the infrared camera. Pit vipers are snakes that have this little pit here. And this pit between the eye and the nostril is an infrared detector. It gives them not so much a clear image, but it gives them directional imaging for heat. So it would be like you guys trying to locate a sound. If you could hear, where's my cell phone? And you turn your head back and forth, you can detect the direction. So these animals can sense their prey's body heat. And the most famous pit vipers, of course, are rattlesnakes. So they don't live in pits. They have what are called L'Oreal pits, not L'Oreal makeup, right? They don't grind these snakes up to make makeup. Though I could start that as an urban legend. It would be pretty funny that L'Oreal grinds up infrared detectors on snakes. Isn't this guy pretty though, eh? Oh, this is a garter snake in California. Notice no pits. It's not a pit viper. Okay. All pit vipers are venomous. Doesn't mean he's not. He's a garter snake, so he'll stink to high heaven if you pick him up. Love